Hello all, welcome to my session on illumination model. In the last session, we discussed about color models, in which we discussed about two basic types of color models, that is RGB color model and CMY and CMYK color models. Right. So the next concept what we will be discussing under computer graphics is illumination model. Right. So what do we mean by illumination? Illumination is nothing but lightning. Right. So it is also called as the lightning model. Right. So as you can see in this particular example, right. So here I have the picture of an object which is a wire frame, right? And this particular picture is without illumination. Without illumination means, right, there is no light incident on it, right? So simply that particular picture is colored, right? So when I have illumination, that means when the light falls on a particular object, right, so we can see that that particular object is illuminated, right? So this particular part of the object is illuminated, right? So that type of model we call it as the illumination model. So an illumination model, it is also called as a lightning model, and sometimes it is also referred to as a shading model, right? So it is basically used to calculate the intensity of light that we should see at a given point on the surface of an object, right? So that means using an illumination model, what we are measuring the intensity of light, right? So that means what is the intensity of a light at a particular point on the surface of an object, right? This is the entire object, but light is incident on only this particular part of the object, right? So what is the intensity of light at a given point on the surface of the object, right? So measuring that or calculating the intensity, we call it as the illumination model. So surface rendering is a procedure, right, that is basically used for applying a lightning model. So it is applied for a lightning model in order to obtain the pixel intensities for all the projected surface positions in a scene, right? So we have to find the intensity of light on this particular point and intensity of light at a particular point, right? So in order to find the intensity of a light, what we are doing is we are making use of a procedure which is called a surface rendering, right? So surface rendering means what? It is a procedure where we are applying a light, right? So in order to obtain pixel intensities, right? So because every surface way is considered as a every picture will be is considered in terms of pixels in computer graphics, right? So what is the pixel intensity for all the projected surface position in a scene, right? So in order to identify the pixel intensities, we are making use of a concept of surface rendering here. So a surface rendering algorithm, it uses the intensity calculations from an illumination model in order to determine the light intensity for all the projected pixel positions for the various surfaces in a scene, right? So in order to determine the light intensity for all the projected pixel positions, what are the different pixels which are present at this particular part of the surface of an object, right? So in order to measure that, we are making use of an algorithm which is called as surface rendering algorithm. So surface rendering, it can be performed by applying the illumination model to every visible surface point. That means wherever you are putting your direct light is incident, right? So in order to calculate the intensity, so we'll be using the surface rendering, right, by applying the illumination to every visible surface point. So in order to do this illumination model, right, so we need some light sources, right? Because without a light, I cannot have any illumination, right? Say for example, if there is full dark, right, and there is no sunlight or no visible light from any sources like tube lights or bulbs or anything, right? So we cannot see anything from that particular object, right? So we need a light. A light is the main source in order to illuminate any object. So light sources, they are also called as light emitting sources and reflecting surfaces, right? So there are light sources are also called as the light emitting sources, and we have one more type of sources which are called as reflecting surfaces. They are the walls of a room. They are termed as the light reflecting source, right? So because how we can see an object can be seen, say for example, when a light is incident on a particular object, right? So there happens an reflection, right? So based on that particular reflection, we can come to know, right, that this is the particular object and this is the color of that particular object, right? So luminous object in general can be both a light source and a light reflector, right? So I can have a I can make use of a light source like sun, like bulbs, right? Like your tube lights, like your table lamps, right? So all those are different types of light sources. I can make use of a light source, or I can have a light reflector, right? So like a mirror which will reflect, right? So in order to illuminate any object. The simplest model for a light emitter is a point source, right? So point source is nothing but your bulb or a sun, right? So which emits light. So there are different mathematical models for light source. We have point source, we have directional light source, and we have spotlight, right? So point source example can be a bulb, right? So which glows and it will provide light. It is omnidirectional, it provides lights in different directions. So sun is also a point source. Directional source, I can call it as a tube light, is an example of directional source because it provides a light in a single direction, right? So next we have the spotlight. Spotlight is nothing but we are making use of a table lamps, right? So or spotlights you have seen in your or a dance or something like that, right? So where spotlights will be is a spotlights you can see, right? So simplest example is your table lamp, where in the complete darkness of a room also you are applying a light, or you are illuminating any object by making use of only that particular spotlight, right? So these are the different types of light sources what we have, right? So coming to the first one, which is the point light source. So point light source example is a sun, or here I have taken a bulb, right? So this is omnidirectional point source because a single source can illuminate a large collection of objects. That means, say for example sunlight, right? So sunlight, right, it makes all the objects which are around it to be visible, right? A person can see all the objects, so it is called as omnidirectional. So we have intensity is referred to by I naught. So position of that particular light source is given by three coordinates, because x comma y comma z coordinate, because the object is placed in three dimensions. So we have px, py and pz, and we have to consider three factors, which are Kc, Ki and Kq, right? So Kc, Ki and Kq are the three factors what we are considering here for attenuation. This is basically for attenuation, right? So we know what do we mean by attenuation. Attenuation is nothing but some disturbance caused, right? So when you are having the light, right? So in order for attenuation, we are making use of three constants, which is nothing but Kc, Ki and Kq, or you can also call it as K0, K1 and K2, right? And what is this? A D? D is nothing but your distance. So I'll write the formula for intensity of a light, because illumination model is basically used to calculate the intensity of light. So intensity of light is given by IL is equal to I naught, that is intensity of the bulb, which is I naught divided by Kc plus Kl d plus Kq d square. This is the formula for calculating the intensity of light using a point light source. The same way we have directional light source, right? So directional light source are it models the light source as infinity, right? So we can take a tube light here, right? So which models the light source at infinity. So intensity is I naught here, and the direction is dx, dy, comma dz, right? So since it is from the sun, there is no attenuation, right? Or with the distance, attenuation is not there. So I will have IL is equal to I naught. So the last type of light source is the spotlight source. So spotlight source is nothing but your light from a table lamp, right? So it models the point light source with direction. That means we are focusing on whichever direction we want. So we have intensity, we have the position, we have the direction, and we have the attenuation factors, right? So the intensity of the bulb, right, or I naught is taken as the product of the distance and also your the incident light, right? So incident light and with the direction. So L and D we are taking. So D into L divided by, this is the attenuation factor, Kc plus K1D plus Kq D square. So when light is incident on an opaque surface, right? So what happens if it is not a transparent object and it is an opaque object? So when light is incident on an opaque surface, part of it is reflected and part of it is absorbed, right? So few part is reflected back and few part is absorbed. So the amount of incident light that is reflected by a surface, it depends on the type of the material. So whenever we want to check what is the amount of the incident light which is reflected, right? So we have to check the surface, right? So if at all the surface is shiny, so shiny materials means they will reflect more of the incident light, and if at all they are dull surfaces, they will absorb more of the incident light. So for an illuminated transparent surface, some of the incident light will be reflected and some will be transmitted through the material. surfaces that are rough or grainy, right? So what they will do, they will tend to scatter the reflected light in all direction, right? So this scattered light is called as the diffuse reflection, right? So we'll be discussing three basic illumination models here, right? So like ambient light, diffuse reflection, and specular reflection, right? So whenever we have the when we have diffuse reflection occurs whenever the light is incident on a rough surface, right? So what happens at that time, that the light is the reflected the light will be reflected in all direction, right? So this light type of reflection we call it as diffuse reflection, right? So in addition to diffuse reflection, we have something called as specular reflection, right? So where light source create highlights or bright spots, that means you are focusing only on a particular point, right? So at that type of reflection we call it as the specular reflection. So this highlighting effect is more pronounced on shiny surfaces than on dull, right? So as we know, shiny surfaces, they reflect more amount of light compared to dull surfaces. So there are three basic illumination models, right? So the first type of illumination model is the ambient illumination. So this ambient light is basically used for uniform lightning, that is, it gives the light which is the same for all the objects. It gives the light which is same for all the objects. It has no space, right? And there is no directional characteristics for the ambient light, right? So in our basic illumination model, we can set a general level of brightness for a scene, right? So this is a simple way to model the combination of light reflections from various surfaces to produce a uniform illumination, right? So wherever there is uniform illumination of the model, that is called as the ambient light, or we can call it as the background light, right? So for example, the light from the sun, it is ambient light, right? So ambient light has no spatial or directional characteristics, and the amount of ambient light incident on each object is constant for all the surfaces and over all the directions, right? So the ambient light which is incident on the object, it is constant for all the surfaces and also over all the directions. The second type of illumination model is diffuse reflection, right? So in diffuse reflection, what happens, we are considering the surface, right? So whenever the light is whenever a light is incident on the surface, right? So that particular surface will absorb some light and it will reflect back the remaining light in all the directions, right? So such type of reflection we call it as the diffuse reflection. So we assume that the diffuse reflections from the surface are scattered with equal intensity in all directions independent of the viewing direction, right? So we are not considering the viewer here, right? So independent of the viewing, in what way you are viewing, right? So whenever the light is incident on any grainy object or any opaque object, right? So at that time, what will happen, that particular the light is reflected in all directions, right? So it is scattered with an equal intensity in all direction independent of the viewing direction. Viewer is not considered in diffuse reflection. So such surface, right, are referred to as the ideal diffuse reflectors, right? So the surfaces which reflect the light in all directions, right? So such surfaces, we call them as diffuse reflectors. They are also called as Lambertian reflectors, right? So why? Because radiated light energy from any point on the surface is governed by Lambert's cosine law. So what is this Lambert's cosine law? So this law states that the amount of radiant energy which is coming from any small surface area, small surface area, right? So which is a dA in direction, right? And phi of n, which is related to the source of normal, is proportional to cos phi of n, right? So the Lambert's law states that the amount of energy which is coming from any small surface area, the amount of light which is coming from here it is the amount of light which is coming from any small surface area in any direction, right? So which is relative to the source of normal is actually surface normal is actually proportional to the cos phi n. So diffuse reflections are actually constant over each surface in a sign. So the fractional amount of the incident light that is diffusely reflected, it can be set for each surface with parameter. We are considering a parameter here which is called as KD. KD is called as the diffuse reflection coefficient or diffuse reflectivity. So this parameter, which is a diffuse reflection coefficient, it can be assigned a constant value in the interval 0 to 1. If we want a high reflective surface, we can set this KD value to 1. This produces a brighter surface with the intensity of the reflected light nearly equal to that of the incident light, right? So, but if I want to absorb, if I want to have a simulate a surface that absorb most of the incident light, then we can set the reflective value to 0, right? So, whenever you want a reflection, more amount of reflection, then you can go for KD value as 1, right? So, when you want lesser amount of reflection and more of absorption, you want it to absorb the more of incidents incident light, then you can set the KD value as 0. So if a surface is exposed only to ambient light, right, we can express the intensity of diffuse reflection at any point on the surface. Say for example, an object is exposed to ambient light. Ambient light means it is uniform light which is distributed on all the types of objects, right? So whenever a surface is exposed only to ambient light, and if I want to calculate the intensity of diffuse reflection, then the formula is I ambient diffuse is equal to KD into IA, right? So where KD is nothing but your diffuse reflection coefficient, right? So and IA is your intensity of the ambient light. So here we have, if at all we denote the angle of incidence, right? So we can see how the reflection happens, right? So we have the incident light, it is incident on any object, right? So whenever the incident light is incident on any surface, right? So there is a reflection, right? So there is a reflection. So if we denote the angle of incidence between the incoming light, right? So and we have a normal, right? So direction of the normal. So normal is always drawn perpendicular to the surface of the object, right? So an illuminated area which is perpendicular, projected perpendicular to the path of the incoming light rays, right? So incident light is hitting an object here, right? So and we are drawing a normal which is 90 degree to that particular surface, right? So and we say that the incident light is making an angle theta, right? Theta. Then the projected area of a surface path is calculated by making use of the Lambert's law, which is nothing but your cos theta, right? So we say Lambert's law states that it is always cosine of the angle, right? So we are taking cos of the angle, we will get it as the area will be equal to cos theta, a cos theta, right? So that is area. So thus the amount of illumination, so whatever the amount of illumination or the number of incident light rays cutting the cross the projected surface path, right? Surface path, it depends on cos theta. So if the incoming light from the surface is perpendicular to the surface at a particular point, then that point is fully illuminated. That means if the incoming light is perpendicular, if the incoming light is directly hitting the surface, then we say that that particular part of the light is completely independent, right? So as the angle of illumination moves away from the surface normal, what happens? The brightness of the point drops off, right? So that means what? If at all I have an incident light which is directly hitting the surface of the object at 90 degree, that means this particular part of the object is highly illuminated. If at all it is hitting at different angles, then what happens? The illumination slightly drops off. So if IL is the intensity of the point light source, then the diffuse reflection equation for a point on the source can be written as IL comma diff is equal to KD into IL cos theta. Right, so a surface is illuminated by a point source only if the angle of incidence is in the range from 0 to 90 degree, right? Because the cos 0 is in the interval from 0 to 1, right? So when cos theta is negative, then the light source is behind the surface, right? So in order to calculate the intensity of the light, right? So we have the equation which is called as the by make use of the diffuse reflection equation, which is given by IL comma diff is equal to KD into IL cos theta, right? So we are taking theta here. Theta is an angle which varies between 0 to 90 degree, because we know that cos 0 is 1, right? Cos 90 degree is 0. It ranges in the interval, right? So it ranges in the interval from 0 to 1, right? So when angle of the cos theta is a negative, then we say that the light source is behind the surface, right? So this is the light source, right? So if at all it is incident, angle of incidence, right, is denoted by the unit light source direction vector L, and the unit surface which is normal, we write it as L, right? So L is nothing but the light, it is nothing but the light source, and N is nothing but the normal to that particular surface. So if L is the unit normal vector to a surface and L is the unit direction vector, right? So L stands to the, L talks about the direction of the incident light, and N is the normal to that particular surface. So if L is the unit direction vector to the point light source from a position surface, then we say cos theta is equal to n into L, right? And the diffuse reflection equation for single point source illumination is given by IL diff is equal to KD into IL into n into L. Cos theta is given by here as n into L. So we can combine the ambient and point source intensity calculation in order to obtain the expression for the total diffuse reflection, right? So many graphics packages, they introduce an ambient reflection coefficient, which is called as Ka, in order to modify the ambient light intensity for each surface. So this simply provides up with an additional parameter in order to adjust the light conditions in a scene, right? So because we know that ambient light means it provides a uniform light for the entire scene, right? So if at all we want to have any reflection coefficients for ambient light, right? Many of the graphic packages, they provide a reflection coefficient for ambient light, which is called as Ka, right? So that we can make use of the ambient reflection, ambient light reflection coefficient, and we can obtain the total diffuse reflection equation as IL comma diff is equal to Ka into Ia plus Kd into IL into n into L, right? So where Ka and Kd are nothing but your coefficients for ambient coefficient and your ambient reflection coefficient and diffuse reflection coefficient, and they both depend on the surface material properties and are assigned the values from the in the range of 0 to 1. The last type of reflection model what we have is called as the surface reflection model, right? So as we know that ambient light means it is uniform light, diffuse reflection means it depends on the surface, right? And it is not considering the viewer, right? But in surface reflection we will consider both the direction, both the surface and also the viewer, right? So the viewer is also a main concern in your specular reflection, right? So a specular reflection is a reflection where we see a highlight or we see a bright spot at certain viewing directions. For example, you might have seen in a dance, right? So if at all we want to have a spotlight, right? So it depends on the main performer, right? So if the main performer moves, as the main performer moves, right? So its viewing direction moves and the light is also moving, right? So specular reflection is one which depends both on the surface and also on the viewer, right? Or we can say on the viewing direction. So this phenomenon is called as specular reflection. It is the result of total or near total reflection of the incident light in a concentrated region around the specular reflection angle, right? So here we are considering a specular reflection angle which is equivalent to the angle of incidence of the light, right? So here L is nothing but the light vector, right? So L is nothing but your unit vector, which is the vector for your directed point light source, right? So and N is the normal for that particular surface, and theta is the angle of incident here, right? So and theta is the angle of reflection here, right? So and R represents the unit vector in the direction of specular reflection. Here we are considering one more vector which is called as V, right? So this V vector is basically used to point the viewer, right? So from the selected surface position, right? So this V, it can be here, it can be here, it depends on wherever he stands and he wants to view the and whichever direction he wants to view the surface, right? So here we can see that the angle of incidence, specular reflection angle of incidence is equal, specular reflection angle is equal to the angle of incidence, which is theta, and viewer makes an angle of phi with that particular with that reflection. So in this figure, we use R to represent the unit vector in the direction of ideal specular reflection. As I have told, L is basically used to represent the unit vector which is directed towards the point light source, and V is the unit vector which is pointing to the viewer from the surface position, right? So and we have an angle phi, right? So which is the viewing angle which is relative to the surface reflection direction, right? So this viewing angle is denoted by phi, right? So this is phi. For an ideal reflector, right? So that is perfect mirror, the incident light is reflected only in the specular reflection direction, right? So in that case, we could only see reflected light when vectors V and R coincide. That means when the angle of theta is equal to 0, right? So when I have a perfect mirror, at that time what happens, the incident light is reflected only in the specular reflection direction, right? So when you have a very shiny, so right, so when you have the corner, when you have a mirror, right, so it is a shiny surface, so at that time what will happen, when the angular the the light is the light which is reflected, that means the angle of incidence which is made by the incident light and the specular reflection angle both will be equal to 0, right? So we can say that the phi value is equal to 0, right? So in order to have the specular reflection, we make use of a model which is called as the Phong model. So this Phong model, what it does is it sets the intensity of specular reflection which is proportional to cos ns of 5, cos to the power of ns of 5, right? So this angle 5 can be assigned values in the range from 0 to 90 degrees, so that the cos 5 varies from 0 to 1, right? And the value assigned to specular reflection exponent, which is ns, it is determined by the type of the surface that we want to display, right? So this ns value for very shine surface, it is modeled with a large value for ns, say 100 or more, and smaller values for ns are basically used for dull surfaces. For a perfect reflector, ns is infinite, right? So this ns is nothing but what? Ns is nothing but your specular reflection exponent, right? So exponent for specular reflection, that is why it is n, yes, right? So specular reflection exponent. For a very shiny surface, this specular reflection value will be 100 or more, and for smaller values which are down to n, and for smaller values which are down to 1, they are basically used for dull surfaces. For a perfect reflector, ns is infinite. So we get finally the right. So by making use of the Spong specular reflection model, right? So we can write the Spong specular reflection model as a W of theta, right? So W of theta, right? So we can approximately model monochromatic specular intensity variation using specular reflection coefficient, right? So we have seen that we are making use of ambient coefficient, which is Ka. We have used diffusion reflection coefficient, which is Kd. The same way we have specular reflection coefficient, which is called as W of theta. So this W of theta, it tends to increase as the angle of incidence increases, right? So using this specular reflection and coefficient, right? So we can, using this spectral reflection coefficient, right? So we can write it as I spect, IL comma spect, which is equal to W of theta into IL into cos to the power of ns into phi. This is the spectral reflection coefficient, right? So this is the Phong specular reflection model, that is I spec is equal to W of theta into IL into cos to the power of ns into phi, right? So since V and R are the unit vectors in the viewing and specular reflection directions, we can calculate the value of your cos theta, that is cos phi. We can calculate the value of cos phi with the dot product of V and R, right? So we can calculate by making use of the dot product V dot R, right? So assuming that the specular reflection coefficient is a constant, we can determine the intensity of the specular reflection at a surface point by using this formula, right? So the formula is I spec is equal to Ks into IL into V dot R into V dot R to the power of ns, right? So here the cos of an angle cos theta or cos phi, the cos of an angle cos phi is replaced with the dot product of your viewing and the specular reflection directions, right? Viewing and the specular reflection directions. So the simplified Phong model, it is obtained by making use of a halfway vector H and L, halfway vector H between L and V values, right? So between L and V, that is the light vector and your viewing vector. Between these two, I'm using one more variable which is called as H, right? So this H is called as the halfway vector, right? So which is between L and V, in order to calculate this basically used to calculate the range of specular reflection, right? So what is the range of specular reflection? So if we replace V dot R in the Phong model with the dot product as n into h, right? So this simply replaces the empirical cos phi calculation with the empirical cos alpha calculation, right? So we are just replacing the cos phi calculation with the cos alpha calculation, and we are having a halfway vector h along the angle between L and V, right? So we get the halfway vector as h is equal to L plus V divided by modulo L plus V, or magnitude of L plus V. So this completes your Phong model. The last type of the model what we have in our illumination is the Van model. This Van model, it basically provides a method for simulating studio lighting effects, right? So we have you people are aware of studio lighting, right? So in order to have studio lighting effects, we will be using the Van model so that we can control the light intensity in different directions, right? So light sources are modeled as points on a reflecting surface using the Phong model for the surface points, right? So using the Phong model, what we are doing, we are calculating the intensity of the light for every point on the surface, right? So then the intensity in different directions is controlled by selecting the values for the Phong exponent, right? So we know that the Phong exponent is ns. So in addition here, light controls and spotlighting are used by the studios. Photographers can also be simulated by using the one model. Using the one model, we can simulate all the studio effects which are basically used by the studio photographers. Flaps are also used to control the amount of light which are emitted by a source in various directions, right? So where flaps are also used in order to control the amount of light which is emitted by any source in various directions. So this completes your illumination model, right? So repeatedly asked exam question is explain the three basic illumination models. You have to write about ambient light. Ambient light is nothing but uniform reflection. Then second type is diffuse reflection. So diffuse reflection means whenever a light is incident on a surface, right, then the light is reflected in all the different directions. That is called as a diffuse reflection, right? So what about specular reflection? In specular reflection, whenever the light is incident on an object on the surface, right, so few of the light is absorbed and the few of the light is reflected, right? And here we are considering both the viewing direction and also the surface of a surface, right, or the object on which the light is incident, along with the viewing direction is considered in your specular reflection, right? So finally, by making use of the halfway vector, right, so which is actually the angle between your unit vector L and the viewing vector, right, so we will be able to reduce the Phong model into the halfway vector as h is equal to L plus V divided by magnitude of L plus V. So this completes your third module. Thank you. So before we complete, we have few OpenGL illumination functions, right? So we have OpenGL point light source function, right? So like GL light name we can give, light property value. So star, in the place of star we can have a suffix code of I or F is appended to the function name depending on the data type of the property value. So for light name we can make use of the light 0, light 1, so on up to 8, so on up to 7. Light property, it must be assigned to one of the OpenGL symbolic property constants, right? So GL enable light time, it will turn on that light with the command, right? So GL enable GL underscore lightning, it will activate all the OpenGL lightning routines. That means if I want to focus light on a particular scene, right, or if I have to drop off the light, or if I have to switch off the light on a particular scene, right, so I can do so by having the OpenGL lightning commands. So the same way we can also specify an OpenGL light source position and type, right? So by making use of the symbolic constant which is GL underscore position, it specifies the light source position. This symbolic constant is used to set two light source properties at the same time, the light source position and the light source type, right? So we have light position, light 1 position type, light 2 position type, right? So we have the light and its position, light 1 position type. I can call the array here, right? So GL enable light 1. If I have to enable the light 2, I will say GL underscore light 2. I will call the position GL underscore position and light 2 position type, and I will call my enable function GL enable light 2. Right, so specifying an OpenGL light source colors. So actually an actual light source and OpenGL, unlike an actual light source, OpenGL also has 3 different color properties, right? The symbolic color property constants are GL underscore ambient light, diffuse light and specular light, right? So GL underscore ambient has a color associated with it which is called as black color, right? So GL underscore diffuse has white color, and GL underscore specular I'm calling with white color, right? So I can also combine the color of the light, right? So whether I want red color light, whether I want white color light or green color light, and what type of light I want, whether I want uniformed light or whether I want a diffused light or whether I want in different direction, that is specular light, right? So all these lighting effects you can do so by making use of your OpenGL lightning functions, right? So this completes your third module. Thank you.